Okay, for our next talk, we have Teogil Moreno de Mora Sardà on the decomposition of complete three manifolds of PSC with quadratic decay.
Yeah, so
Oh,
thank you.
whenever you're ready. Yeah.
Yeah. So thank you for the introduction and also for the opportunity to speak in this workshop. And so today I wanted to talk about a result about the topology of uh, complete or of three-dimensional manifolds that admit complete metrics of positive scalar curvature. So it will have some similarities with talk. And this is joint work with Florent Balachev and Stéphane Saboureau. And before starting, yeah, just feel free to interrupt me whenever you have a question or a remark. Okay. So let us start by fixing or by considering a three-dimensional Riemannian manifold. And during the talk, all the manifolds that I'll consider will be orientable and with empty boundary. And also the Riemannian matrix will be considered complete. And the question that motivates this talk, that appeared also in the previous talk, is the following. Can we understand or can we determine which three-dimensional manifolds admit complete Riemannian matrix of positive scalar curvature? And these manifolds are known in the literature as PSC manifolds. And in particular, this question appeared, for example, in Yau's problem section. So it is, in full generalities, is still an open question, and it's okay. So let me start by reviewing the closed case that appeared also in the previous talk. And as it was mentioned there, orientable every orientable closed PSC three-dimensional manifold is homeomorphic to a finite connected sum of spherical manifolds, that is quotients of the three sphere by a finite subgroup acting by isometries and freely on S3, and some finitely many S2 cross S1 terms. So this theorem is a consequence of, in the converse direction, is a consequence of the well-known surgery theorem by Schoen and Yau and Gromov and Lawson, which tells us, the statement is more general than that, but this is what we will use in this talk. It tells us in particular that if we have two manifolds that carry metrics of positive scalar curvature, and you take their connected sum, the resulting manifold, or the manifold that you obtain, is again a manifold, a PSC manifold. So it also admits a metric of positive scalar curvature. So since spherical manifolds and S2 cross S1 all are PSC manifolds, their connected sums will also be a PSC manifold. And in the direct direction, this follows from the work of Schoen and Yau and Gromov and Lawson again, and with the contribution of the works of Perelman. So let me just say two words on that. Suppose that you have M, a closed orientable three-dimensional manifold. There's a classical result in three-dimensional topology that tells you that this manifold decomposes or is homeomorphic to a finite connected sum of prime manifolds. So a prime manifold is a manifold that only admits the trivial decomposition in connected sums, meaning that if it is homeomorphic to a connected sum of two manifolds, one of them must be the three sphere, which recall that acts as the neutral element by the connected sum. So this is a classical result in three-dimensional topology, and after Perelman's resolution of the geometrization conjecture, these prime closed orientable manifolds are actually classified. And if you have such a manifold, then if the fundamental group of P is finite, then you have exactly a spherical manifold. If the fundamental group is infinitely cyclic, then P is homeomorphic to S2 cross S1, and otherwise P has to be aspherical. And that means that its universal cover is a contractible manifold, or equivalently, if you want, that all its higher homotopy groups vanish. Okay, so with this, after Perelman's works, we can now write M. We can always express M as a finite connected sum of spherical manifolds, S2 cross S1 products, and aspherical terms. And then the actual contribution of Schoen and Yau and Gromov and Lawson was to rule out the appearance of these aspherical terms if the manifold M admits a metric of positive scalar curvature. So this closes the case of compact or closed PSC three-dimensional manifolds. And let's now discuss the open case, so for non-compact manifolds. And the first thing that we should do when considering non-compact manifolds is to extend the notion of connected sums in order to be able to consider manifolds that have infinitely many terms. And this is done, or this is called an infinite connected sum along a graph. And it's a notion, I forgot to write it here, but it's a notion due to Scott from the 70s. And the construction goes as follows. So first, we need to fix G, a locally finite graph, meaning that all its vertices have a finite degree. We fix also F, a family of three-dimensional manifolds that we can consider to be closed and orientable. And we do the following. So for each vertex V in our graph, we consider a manifold which belongs to the family F. And we do this for every vertex in our graph. And then for each edge joining two vertices, we will take the connected sum of the corresponding manifolds. And we will obtain something of this. So we will say that an open or a manifold, a three-dimensional manifold, decomposes as an infinite connected sum if it can be obtained by this procedure. And there's an equivalent way to see that. M decomposes as an infinite connected sum if it exists or it admits a locally finite collection of embedded disjoint spheres. So the spheres would correspond to the edges of the graph, and we need them to be, or we need the family to be locally finite. So because what we want is that if we cut our manifold, the resulting manifold, or the manifold, sorry, along this family of spheres, we want that the resulting pieces are all compact. So they are that they are all a manifold. Sorry. So we need this family to be locally finite. So two remarks on this notion. The first one is that whenever G is a finite tree, we recover the classical notion of connected sum. And that actually by adding the manifold S2 cross S1 to the family, if it wasn't already there, we can always assume that the graph G is a locally finite tree. We can kind of like undo the loops on the graph by just adding S2 cross S1 terms to the connected sum. So a natural question when considering this more general notion of connected sum is whether we have or not an analog of Nether-Milnor's decomposition for open manifolds. That is, can we always decompose an open manifold as an infinite connected sum? And if we can do that, are these decompositions unique? And the answer to these questions is that actually this notion is not very well behaved. So regarding existence, it was proven originally by Scott in the 70s, but also more recently, there were new examples given by Maillot, who constructed open manifolds that do not admit a decomposition as an infinite connected sum of closed manifolds. So not every manifold decomposes as an infinite connected sum. And regarding uniqueness, it is somehow subtle. Even if we consider all those manifolds that decompose, so the resulting manifold obviously depends on G, and actually we can by choosing different graphs we can obtain the same manifold. So already there's something weird depending on the graph. But even if we fix the graph, there are some funny phenomena like the following. So if we have this alternate connected sum of non-homeomorphic prime manifolds, actually you see here that even if the proportion of the prime terms that appear is different, the two manifolds are homeomorphic, which is quite funny. Whereas in the second row, we have exactly the same numbers of each prime factor, but the resulting manifold they are not the same. But it turns out that if we assume further hypotheses on the topology of M, and more precisely through or if we assume a condition on the scalar curvature of M, we will be able to ensure that that the manifold M decomposes as an infinite connected sum. And this was proven by Gromov and by Wang independently in 2023, who proved that if you have an orientable complete Riemannian three-dimensional manifold of uniformly positive scalar curvature, so such that the scalar curvature is bounded away from zero by a positive constant, then M it decomposes as a connected sum of spherical manifolds and S2 plus S1 terms. And here, this connected sum is possibly infinite. And what I mean by this notation is that there is a locally finite graph such that M can be constructed as an infinite connected sum along this graph on the family of spherical manifolds and S2 cross S1. So Gromov and Wang's proof relied, as he said, on mu bubbles, so a very analytical approach. And a natural question after this theorem would be, at which point can we relax this hypothesis on the scalar curvature, but still be able to ensure that M decomposes as an infinite connected sum of spherical manifolds and S2 cross S1 products? And together with Florent Balachev and Stéphane Savoureau, we found that if you have an orientable and complete Riemannian three-dimensional manifold M, which has positive scalar curvature, which decays not too fast at infinity, so such that decays at least at most quadratically with the distance to a certain point x on M at infinity. And here the constant C also cannot be too small. Then you can still ensure that M decomposes as an infinite connected sum of spherical manifolds and S2 cross S1 terms. So obviously this result includes the uniformly positive scalar curvature case, so the Gromov and Wang case. And moreover, we found that this result is sharp in the decay rate. So there's also this example that appeared in the previous talk of the manifold R2 cross S1, which does not admit such a decomposition, cannot be decomposed as an infinite connected sum of spherical manifolds and S2 cross S1 products, but which admits a complete metric, whose precise expression I have written here, but it is exactly the manifold that appeared in the previous talk. So you have something that looks like a parabolic in the R2 term, and then you have just the standard metric on S1, and you take the product metric. So for this product metric, the scalar curvature decays exactly quadratically at infinity, and therefore it gives kind of like it shows that this result cannot be improved in terms of the decay rate. Also, another, I haven't written it here, but another consequence of this theorem is that we have some kind of rigidity, because if your manifold admits the metric of positive scalar curvature decaying in this fashion, then you can also this manifold also admits a metric of uniformly positive scalar curvature. So it is immediately as in the class of manifolds that were obtained in Gromov and Wang's result. Okay, so during the rest of the talk, I'll talk about the proof and the techniques that we use to obtain this result. And the key remark on the proof of this result is based on the following theorem by Gromov and Lawson. So suppose that M is an orientable and complete manifold which has uniformly positive scalar curvature. So where the scalar curvature is bounded away from zero by this S0 constant. Then they showed that every contractible curve lying on M will bound a disk in a controlled metric neighborhood. So it will bound a disk which is contained in the neighborhood of radius 2 pi over the square root of S0. So it will be at most a distance 2 pi over the square root of S0 from gamma. Whenever a contractible curve gamma satisfies this condition, I'll write that the field radius of gamma has this upper bound. And since this property holds for every contractible curve, I'll just write that the field radius of M is bounded by this quantity. So what Gromov and Lawson's theorem tells us is that if we have a lower bound on the scalar curvature, we immediately get an upper bound on the field radius of curves on the manifold. And actually it tells us something weaker than that, because just by lifting the Riemannian metric of on the manifold M to the universal cover, we get again a lower bound on the scalar curvature of the universal cover, and therefore we can conclude that the field radius of curves in the universal cover is bounded by this constant. And this is meaningful because notice that if our manifold M is compact, for instance, actually the field radius of M is trivially bounded by its diameter, but we can still say something about the universal cover of M, which may not be compact, for example. So based on this theorem, we were able to prove, or we were able to extend this theorem to the quadratic decays case, just by applying the result on metric balls growing in radii on our manifold. So we found that whenever you have not a uniformly positive scalar curvature, but positive scalar curvature decaying quadratically at infinity, then this implies, by the same argument of Gromov and Lawson, that the field radius of the universal cover of M is or grows at most linearly with the radius. And here the constant, so this holds for a C that is not too small, and also so the constant that we have here gives us a certain constant C prime on the control on the field radius. So I haven't written it here. This kind of notation was a little bit maybe imprecise, but what we precisely mean by this is that every curve contained in a metric ball of radius R, which is contractible in M, in the base manifold, has field radius bounded by this constant, by this quantity that depends on R, the radius of the metric ball where gamma light. And again, if you want for these technical reasons, or because it's actually more meaningful to us, we don't consider, so we don't look at the field radius of the curve gamma, but rather the field radius of a lift gamma tilde of gamma to the universal cover of M. And actually what we do is we just forget about any assumption on the scalar curvature, and we just assume this growth control on the field radius that will serve as a kind of a synthetic notion for this condition of PSC with quadratic decay at infinity. So actually we were able to prove this result without any curvature assumption, and just by considering this more general hypothesis on the field radius of curves in the universal cover of M. Okay. So we will use these more general hypotheses, and now let me explain how do we prove this decomposition. And the proof will kind of resemble what Yiz did in the previous talk, but so we will actually construct an exhaustion of our manifold M by compact sets. But actually, we will not need to do it by any geometric flow. We will just exhaust it by metric balls, and then we will perform some modifications on this exhaustion to make it be what we want. So let us consider the point X on M, and what we will do, as I said, is we will exhaust our manifold by metric balls of increasing radii tending towards infinity. So this will give us as a sequence of compact subsets that will exhaust entirely our manifold M, and whose boundaries up to slightly moving the radii Ri will all be embedded surfaces that I'll denote that I have denoted here by sigma. So so let me first assume that all these sigma surfaces are homeomorphic to the two-sphere, and then I'll explain how do we prove how we will prove this assumption. But let me first just assume it. Then if they are all spheres, what we can do is we can cut our manifold along these two spheres. This will leave us a collection of compact manifolds with some boundary components that are a finite collection of spheres, and that I have denoted here by Y. And then what we can do is we can cut off each of these resulting compact pieces by gluing, so we can glue a 3 ball along the spherical boundary, or along each spherical boundary of these pieces, to get actual closed 3-dimensional manifolds, which here are denoted by Y hat. So actually, this procedure or this assumption on the surface is sigma. What allows us to do is to decompose our manifold M in as an infinite connected sum of closed manifolds, Y hats. And the graph that realizes this infinite connected sum is the obvious one. So what we are actually doing is we're placing a vertex at each compact connected component, and then we're joining two vertices whenever they share a surface, or whenever they come from the same surface sigma from the exhaustion. And since these manifolds Y hat are all closed, we can apply Nether-Milner's decomposition theorem to express them as a finite connected sum of prime manifolds. And the second thing that we want to ensure is that none of these manifolds contains an aspherical term in their Nether-Milner decomposition. So we want all these p's to be non-homeomorphic to a spherical manifold. And we will actually prove these two assumptions using our more general condition based on the field radius of curves, or of lifts of curves to the universal cover of M. Okay. So maybe I should stop here to ask if someone has some question about what. Okay, if not, I'll continue, but just feel free to interrupt me if you have any question. Okay, so as an intermediate step of the proof of the theorem, we obtain the following result. Let M be a complete Riemannian manifold, and here this result holds actually for any dimension. So let M be a complete Riemannian n-dimensional manifold, and assume that the field radius of the universal cover has this linear growth control. And here the constant C prime cannot be greater than 1/3. So the growth has to be not too fast, which corresponds to the decay not too fast at infinity, the decay of the scalar curvature. So assume that you have such a a cross control on the field radius of the universal cover. And then what we can prove is that every finitely generated subgroup of the fundamental group of M cannot have exactly one end. So here the E denotes the number of ends of the group G. And just recall that for a topological space, the number of ends counts, informally counts the number of connected components of infinity. So here for this example, for this surface, the number of ends would be 3. And then if you have a finitely generated group G, you can define the number of ends of G as the number of ends of its Cayley graph. So as you know, the Cayley graph depends on the generating set that you choose to construct it, but actually one can prove that the number of ends of the Cayley graphs does not depend, the number of ends does not depend on the generating set. So this notion is actually a group invariant, and it is well defined. So actually it was proven a long time ago that as opposed to the number of ends of a topological space, the number of ends of a group cannot take any non-negative number, but it can only take values in the set of 0, 1, 2, or infinity. And there's another interesting property of the number of ends of a group, which is the following. If you're computing the number of ends of the fundamental group of a closed manifold, then it is given by the number of ends of its universal cover. But it only works when the manifold M is closed. So this assumption is really important. Okay, so this result is a generalization of something that was already proven by Gromov and Lawson in 2009, who proved it for closed manifolds, and when what we have is a uniform bound on the field radius of curves in the universal cover. And I'll just say so the proof of the more general theorem is quite technical, but the idea is the following. So if the fundamental group of M has a finitely generated subgroup with exactly one end, we're able to construct for every R large enough, what we are able to do is to construct a closed curve in the universal cover of M, whose field radius grows faster than 1/3 times the radius R. So that violates the hypothesis on the control on the field radius. And in order to do so, in full generality is a little bit complicated, but there's also in like the simpler case, it can give like an insight of how we do it. So let us assume that G contains an element which is of infinite order. And what we do is we represent this element by gamma a closed geodesic. And if M, so here also it's in the closed case. So assume that M is closed and that we can represent this infinitely ordered element by a closed geodesic. And then what we can do is we can lift it to the universal cover. We can fix a point on this curve, an arbitrary point, and we can consider a metric ball of radius r centered at this point. And by using the hypothesis that G has exactly one end, we're able to, this means somehow that the two ends of this curve can be joined by a curve. And the resulting curve, which is at R, it can be proven, or we can prove that this curve cannot be filled by a disk not going too far away from it. So we can prove that this curve at R satisfies this inequality. But again, so in the general case is much is more technical than that. Okay, so we have this result that implies a condition on the subgroups of the fundamental group, and by using a standard argument from Basler theory, actually what we can prove is that the fundamental group is virtually free, meaning that contains a finite index subgroup which is free. Another consequence of this result is that actually our manifold cannot be expressed cannot be homeomorphic to the connected sum of any manifold with a closed spherical manifold. So in particular, this will rule out the possibility of having aspherical terms in our decomposition in the original theorem. And how do we show that? So actually, if M is of this form, the fundamental group of K will be a subgroup of the fundamental group of M. And one can show that the fundamental group of a closed spherical manifold has exactly one M, because the universal cover of K is a contractible manifold. And so contractible. And this contractible manifold will also have one end. So we can use the previous property to show that the number of ends of the pi1 of K will be exactly one, which would contradict the conclusion of our theorem. And this is related to a well-known conjecture in scalar curvature geometry, which states that closed spherical manifolds do not carry metrics of positive scalar curvature. And actually, this conjecture was proven it was proved that it was the case by Gromov and Lawson in dimension 3. And then recently it was also proven by Chodoj and Lee for dimensions 4 and 5. But it remains open for higher dimensions. And actually, there's another related conjecture to this one, which states that closed Q-essential manifolds do not carry metrics of positive scalar curvature. And here, by Q-essential, I mean that it admits a map, a continuous map, to an aspherical manifold, which induces a morphism in top rational homology, which is non-trivial. And obviously, so every aspherical manifold is immediately also Q-essential. So actually, this conjecture is more general. This Q-essential conjecture is more general than the aspherical conjecture. And as a corollary of our theorem, we obtain that if M is a closed n-dimensional manifold, whose universal cover has uniformly bounded field radius, then M is not Q-essential. So even though in higher dimensions, so in dimension 3, this condition is implied by M having positive scalar curvature, but in higher dimensions, we don't have an equivalent of Gromov-Lawson's theorem. But what this corollary tells us is that this synthetic notion based on the field radius of curves kind of points in the right direction. So it kind of recovers some things that we expect to be true for scalar curvature. Okay, so so what we have to do now is to show that coming back to the proof of the main theorem, what we need to prove now is that this growth condition on the field radius of contractible curve or of curves in the universal cover implies the two assumptions that we did when we decomposed M as a connected sum. And we will use this intermediate theorem that I have presented before. So as I've said, the easy maybe the easiest of the two is the second point. So what we want to show is that none of these y-hat terms that we decomposed them into has an aspherical term, and this follows from the exact same observation that I did before. So if your manifold M or if one of these y-hats had an aspherical term, this would mean that your manifold M could be written as the connected sum of N, a non-compact manifold, with K, a closed aspherical three-dimensional manifold. And immediately this would violate, or this would contradict the conclusion of our previous theorem. So this is not possible. I mean, so this is not possible, and we have the second assumption holds for our hypothesis. And so how the last step of the proof is to show that all these sigmas are spheres, and we need to distinguish between two different cases. So let me start by assuming that sigma is what we call incompressible in M, meaning that the morphism induced by the inclusion of sigma in M at the level of the fundamental groups is injective. So if this morphism is injective, that means that the fundamental group of M contains a subgroup which is homeomorphic to the fundamental group of sigma. By our theorem, this cannot have exactly one end, but the only surface that satisfies this condition is the two-sphere. So we immediately get for incompressible surfaces that sigma has to be a sphere. And so what happens if sigma, our surface, is compressible? So if this morphism is not injective, we can do the following. So if this morphism is not injective, this means that there is a curve gamma, which represents a non-trivial element of the kernel of the map. And actually, geometrically, what this means is that there is a curve gamma which bounds a disk in M, but does not bound a disk in sigma. And by a classical theorem of three-dimensional topology, actually we can always find a curve and a disk such that the disk is embedded. And this is guaranteed by the loop theorem that was proven by Papakyriakopoulos in the 50s. And this is important. We need the disk to be embedded because now what we can perform whenever we have an embedded disk, we can perform what we call a compression of sigma. And this consists in cutting our sigma along a tubular neighborhood of the curve, and then gluing a copy of the embedded disk at each side of the cutting. So since the disk is embedded, we can ensure that this new surface, that it should be sigma prime, it is again a surface. And actually, so by applying this compression procedure finitely many times, what we can do is we will be able so we will transform our original surface sigma into something that is incompressible, and then it will be immediately a two-sphere. But there's a little thing that one has to pay attention to, which is the following. So recall that these sigmas were the surfaces that bounded the different compacts that exhausted our manifold. So in the right hand side, I have the picture that I draw before. And these two pictures are different. So here in the right hand side, let me fix a surface sigma I, and here the surface is depicted in red here, and it separates something that is bounded in the left hand side from something that is unbounded in the right hand side. And in the left picture, the surface, the two genus surface, if you want, depicted by red is the sigma, the surface sigma that I'm considering, and it separates its interior, which would correspond to this bounded part of our manifold, from the exterior, which corresponds to the unbounded part. So what we're actually doing when we compress our surface sigma I along a compression disk is actually what we're doing is we're removing a piece we're removing actually a cylinder from the compact or from the metric ball of radius Ri, and we're adding it to the next step of the exhaustion. We're adding it to the ball of radius Ri plus 1. So actually it could be problematic that these compression disks that we're using, along which we're modifying our exhaustion to make these sigmas, to turn these sigmas into spheres, it would be problematic that they entered previous steps of the exhaustion. So actually we could have something, yeah, like this disk here that went very far away and actually entered some previous steps of the exhaustion, and then this would imply that when performing a compression along these disks, we could end up with some sequence of compacts that would not exhaust our manifold to infinity, and we don't want that. So here again, we use our condition, our synthetic PSC condition, which is formulated in terms of the field radius of contractible curves. And actually what we can do is, so recall that these compact sets were metric balls of a certain radius, Ri. And what we can do is we can select the radii so they are separated enough in order to guarantee that the filling disks that the filling disks don't go too far away from the original curves. So, and we can guarantee that the filling disks don't enter previous steps of the exhaustion. So if we have, for example, a uniformly positive scalar curvature condition on the original manifold, this would imply a uniform bound of the filling radius, and this it would be enough to take the metric balls evenly spaced with a distance that is larger than this uniform bound. In the more general case, where what we have is a quadratic decay of the scalar curvature, so what we have here is a linear growth on the field radius. We cannot take these balls to be evenly spaced, but still we can play with the radii to be able to ensure that we have that the compression disks remain metrically controlled and that they don't interfere with the previous steps of the exhaustion. So here we use again our synthetic hypothesis of positive scalar curvature to solve this problematic. And yeah, this concludes the proof, and this is everything that I wanted to say. So thank you very much for the attention, and yeah, if you have any questions, I'll be happy to answer.
Okay, so yes, does anyone have any questions for our speaker? Okay, so I do have one. So back in when you were stating the theorem, you
Sorry, you muted. Sorry, yeah.
there. Um, so you had the example of the S1 cross R2, and you said this made it optimal for decay, right? So both were decaying at R squared or 1 over R squared. It was the constants that were different. Is that what?
Yeah, exactly. Yes.
So do you expect to be able to drop the right, your constant was much larger than 1/2 or something, right? If I remember.
Yeah, right. Yeah, so yeah, that's something that yeah, so there are several steps where we yeah, so the existence of kind of like a critical constant is conjectured by Gromov.
Mhm.
And yeah, so we don't reach this, so we don't have optimality in the constant. And yeah, there are several like sources of non-optimality on our result. And the main one kind of is contained in this theorem that allows us to yeah, to say something about the
So
groups of the
so it's the
fundamental.
constant with the fill radius is what's going. Would you say
Yeah,
is the most egregious one or something? Yeah.
yeah. So actually, this bound on the constant of the field radius corresponds to a lower bound on the constant of the scalar curvature, because those two
Mhm.
are related. So yeah. Everything you can
Gotcha.
yeah, because so yeah, in this translation from scalar curvature to field radius, there's also the constant that we used is actually 2 pi over the square root of S0, and actually this constant was improved. So already Schoen and Yau gave a better constant for this fact, because this result was also I forgot to say them, but yeah, it is due also to Schoen and Yau. Sorry. And actually, it was proven that it's optimal. This Schoen and Yau constant, but actually we could not adapt it so easily to extend to be able to extend it to the decrease case. So we used only the Gromov and Lawson constant. So maybe there is also like something that could be done there.
Gotcha. And do you remember what the conjectured constant is? Is it the one for that metric on the R2
It's
times
not,
S1?
I don't remember the precise value, but it's not the, if I remember correctly, it's not the one given by
Okay.
R2 as well. Yeah. Yeah. So maybe
Yeah.
there are other examples of metrics on R2 cross S1 that increase this.
Yeah, larger, yeah.
Yeah. But we will never be able, as a consequence of this theorem, you will never be able to endow it with a metric whose scalar curvature decay is slower than this critical constant that we obtain.
Okay, yes. Thank you. Thank you. Yeah.
Thank you.
I have a question.
Yeah.
So why you introduce the notion of Q essentialless in your previous screen?
Yeah.
It does not seem to be used in the proof.
No, it's not used. It's just if you want, it's a corollary of. So it has, yeah, we don't use that. We obtain it as a corollary, and actually so we derive. If you want, what we obtain as a consequence of this theorem on the number of ends of subgroups of the fundamental group of M is that closed Q essential manifolds do not admit metrics whose field radius is uniformly bounded. But
Okay.
if you want it.
So maybe your main result can be regarded as a non-compact version of Q essential. Your condition that the field radius is linear bounded.
Say it again. Sorry. So our main result it would be.
Yes. I mean maybe I'm not very sure about that. I just think maybe your condition that the filling radius is bounded from 1/3 times R maybe regarded as a non-compact version of the Q essential.
But here it's for closed manifolds.
Oh yeah. So maybe I can interpret it like this. If you have a non-compact manifold and its filling radius is bounded from below by a constant times R, then it is Q essential in some sense.
Um, uh, but that's not, yeah. So I think that's not the case because, for example, if you drop the closed assumption here, the conjecture is no longer true. So for example, R3 admits the metric of positive scalar curvature.
Oh yeah, yes. So you need a linear control in non-compact case.
What do you mean by that? I mean, R3 also admits a metric decaying. If you want, R3 admits a metric of uniformly positive scalar curvature as a result of our theorem as well.
Maybe that does not make sense. I will think about it more. Yeah, thank you.
Okay, thank you.
Sorry, I have a small question. I don't know again if it is reasonable, but when you have boundary, since if I understand it, okay, it is without boundary. But if you have a boundary, you can say something in some cases, or it is a simple case when we have boundary.
I mean, if you have boundary, I think that you have to admit to say something. So you have to impose some condition on the boundary because otherwise you can easily like endow your manifold with a metric of positive scalar curvature. I don't know. So yeah, I don't know what you have in mind exactly.
Yes, I think if I don't remember if you have some boundary condition, maybe you can use the double and apply your result.
Yeah.
So let me just make a quick comment on this. So there's a result of Carlotto and Lee that says if you're a three manifold with positive scalar curvature, it's a three manifold with boundary, positive scalar curvature, and mean convex boundary, then you have a classification. You're a connected sum of handle bodies and then the things from the closed case too. So this was 2021, 2023, something around there. I think the name of the paper is Constrained Deformations, and then something else, but that should be enough information if you're trying to find it, I think.
Paul, sorry, but is compact or not? The case that treat Carlotto.
I guess that one is compact, yes. So you're asking for you have non-compact boundary, non-compact
Yes,
boundary.
non-compact, since you need to use this result in some sense. Okay, thank you.
I'm not sure. Maybe there's also something to think there, but I don't know.
Yes, I don't think it is so direct. So thank you.
Okay. Are there any last questions? I mean, we still have some time if people want to, or comments or anything. Okay, if not, we'll thank the speaker again and I'll end the recording.
Thank you.